Okay, so we're going to take a look at each one of the ones that we had just listed. So enthalpy of a solution, phase change, chemical reactions, nuclear reactions. Obviously, we're going to spend a lot more time looking at chemical reactions throughout the rest of this chapter, but we'll talk a little bit about each one today. Okay, so enthalpy of a solution. So this happens whenever you have a substance that's dissolving into a solvent, right? So a solute dissolved in the solvent. So when you have something as simple as, let's say we take sodium chloride and dissolve it, you have to understand there's several things that are happening. So first of all, the forces or bonds between the solute molecules or ions will have to pull apart. So meaning if I have a sodium chloride, let's say, the ions have to dissociate. So meaning the ions have to pull apart from one another. That takes energy. The solvent molecules have to have the forces pull apart. So let's say we were looking at water. Water has forces of attraction, right? We know it has dipole-dipole, and it has hydrogen bonding, and it has LDF. So in order to pull those waters apart to make room for the ions, that takes energy. Bonds between solvent molecules and solute molecules or ions are formed. So this actually should say bonds or forces. You're not really making a bond. It's actually just the attraction between solute and solvent that are going to come together once the solution is fully dissolved. This actually will release energy. So when we're looking at the change in enthalpy for this entire process, the enthalpy of solution, we're looking at all these different components together. Like, what is the overall change in enthalpy? So here's a graphical kind of diagram to show you the process. So just to explain, you're going to see a lot of these graphs. So the x-axis is always, think of this as like, almost like time, like the process at the beginning, and then the reactants, and then as you go ahead forward, and then the products are always at the end, right? So it's kind of like as the process is happening. Your y-axis in this case is enthalpy or energy. Okay, so this point here, this black line, is the initial energy that those reactants have. So notice we have a solute, and we're trying to dissolve the solute in the solvent, right? But remember, even before we do anything, particles have potential energy. So they do have some amount of initial energy. When we put the solute in the solvent and we want the ions to separate, that takes energy. Energy has to be put in to pull them apart. Think of like little mini magnets that are all together. If you want to pull those magnets apart, you need to put an effort in. Energy has to be involved to pull them physically apart. The solvent forces of attraction, so imagine these are waters, right? In order to separate them to make room for the ions, that's going to take a certain amount of energy. So energy had to go in. So notice this line here. This is showing you that all the energy that had to go in is both the solute energy and the solvent energy. So let's say this was 10 joules and this was 5 joules. The total amount of energy that had to be put in is 15 joules, positive 15 joules. Now, the solution, once they all mix together and you have new forces of attraction, energy is released. So let's say, for example, 20 joules of energy was released when that happened. And we end up with a final amount of energy for the product amounts. So this is like the potential energy within the products. Well, the overall change is this. The initial point of energy in comparison to the final point of energy. Now, how do we get this overall energy change? You have to look at all the little steps that involved. The solute was pulled apart, the solvent had to get pulled apart, and then we had to mix them together. So let's say we had 15 joules of energy that had to go in. 20 joules of energy had to go out. So that actually would tell us that the resulting overall change would be -5 joules worth of energy. More energy came out than the energy that had to go in. This actually is what's telling us that we have an exothermic process. So an exothermic process means more energy came out of the system than energy that had to go into the system. If it was the opposite, let's say more energy had to go in than the energy that came out, then you would have an endothermic process. So I want you to notice something. The delta H, when you have an exothermic process, is negative. If you were to have an endothermic process, the delta H would be positive, okay? So negative delta H essentially means energy had to come out of the system. Where did this 5 joules go? It went into the surroundings. Any energy exchange, remember that we're looking at, is from system and surroundings. So if we're saying, oh, 15 joules had to go in, where did this 15 joules of energy come from? From the surroundings. 20 joules of energy came out. Where did this 20 joules go? To the surroundings. So when we're looking at the overall for the whole thing, you're really looking at how much went in versus how much went out. Overall, in this particular example, more went out than what went in. Okay, phase change. So looking at change in state. Okay, so every enthalpy value, or I should say process that you're looking at, has a little like name for it. So if you noticed here, it's like enthalpy of solution. Okay, so you can have enthalpy of melting, enthalpy of evaporation, enthalpy of freezing. Okay, you can have a delta H of any process. And it's just kind of like it's almost like you're just labeling what it is. To be honest, even if you just said delta H, it's the same thing. They're just being specific. Hey, this is delta H for melting. Okay, so let's look at state change. So when you're going from solid to liquid, right, this is enthalpy of melting. Liquid to gas, enthalpy of vaporization or also evaporation, same thing, right? If you're going from gas to liquid, it's condensation, enthalpy of condensation. And then if you are going from liquid to solid, it's enthalpy of freezing, or sometimes this is also referred to as enthalpy of fusion or solidification. Okay, same thing. I want you to notice the change in enthalpy. So when you are melting or vaporizing, the delta H values are positive. Right, so notice the arrow is going up. Right, here's our final, here's where we started. Energy had to go in. Energy had to go in. If you're going the opposite, you have negative delta H values. Negative delta H. Here's the initial, here's the final. Energy had to come out in order for it to go from a gas to a liquid. In order for a liquid to become a solid, energy had to come out of the system and go into the surroundings. So technically, these processes on the left here are endothermic processes. So we need to add energy in from the surroundings. The processes on the right are exothermic processes, which means energy is released into the surroundings. Okay, and of course, one thing that is not shown here is going straight to a gas. That is delta H for sublimation. Sublimation. Okay, and that goes actually both ways. Sublimation can go in the positive, so depending on if you're going from a solid to a gas or a gas to a solid. Okay, so as I mentioned, so enthalpy of chemical reactions, we're going to be spending a lot more time looking at that throughout the rest of this chapter. So enthalpy of chemical reactions usually is just written with a little r, like R for reaction. You know how over here they have like melting or vaporization. here it's just delta H of a reaction. Okay, so delta H of a chemical reaction is different for every reaction, of course, and usually we reference the number of moles that are reacting. Okay, so for example, just to recap, remember that the coefficients in front of a compound is technically the molar ratio for that compound. So here we have 1 mole of methane, 2 moles of oxygen, 1 mole of carbon dioxide, and 2 moles of water. So for this particular example, let's say we had 1 mole of methane combusting, it would actually give off negative 890 kilojoules overall. So this is definitely an exothermic process, right? Because it's a negative delta H. So I'm not going to spend too much time going over this because we're going to spend a lot of time in the rest of the chapter here. Enthalpy of nuclear reactions. So majority of nuclear reactions are exothermic. So notice energy is written on the product side. There's not really too much that I need you to know from this. You should know that when you're looking at the radioactive decay, like if I gave you this reaction, you should be able to recognize that this is nuclear decay, right? So here you have an alpha particle and here you have beta. This goes back to grade 11. But essentially, just so you know, kind of the way that it's written, and they are exothermic processes. Okay, so in general, and this is actually a great, I know I've talked about this already, but in general, whenever we talk about enthalpy change, we are referencing the system, okay? And typically when we are referencing heat, we are looking at the surroundings. Okay, so remember that all energy exchange between system and surroundings cannot be, they can't disappear or come out of nowhere. So if energy is lost from the system, it is gained in the surroundings. If it is gained in the system, it had to have come from the surroundings. So overall, for an endothermic reaction, the Q value should be negative. The surroundings are getting cooler. So the change in temperature would be negative as well. The delta H is a positive. If you have an exothermic process, the Q is positive, which means delta T is positive, right? Which means the surroundings are getting warmer. This should make sense, right? The delta H is a negative.